Let me begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for these students. I just ask that you'd guide our steps today. Help us to glorify you in what we do, Lord. In your name I pray. Lord Jesus, amen. Okay, so, yeah, without further ado, I will share the bait that Dr. Sprano left me. I'm not going to work this problem unless we have time at the end, but this is a challenge problem, I imagine. X times inverse tangent of x. Oh, wait a minute. Nope. Square root of x dx. So, Dr. Sprano. Gift. All right. So, let's talk about integration by parts a little bit more, right? So, integration by parts last time, or IBP as we call it, it says what? It says the integral of u dv equals what? uv minus the integral of v du. So, one of the problems I tried last time, but I gave up on, right, because I thought we were going to get nowhere, was what? Remember we tried to integrate secant last time, right? And what happened? Using integration by parts on secant. I'd like to revisit that example just for a second because it's illustrative of something. So let's just go back through that real quick. So if we make this my u and this my dv, what's v? Well, v is x then, right? So I get x secant of x minus the integral of what? v du, which in this case would be what? X. What's my du? What's the derivative of secant? Well, it's secant tangent, right? So I have secant x tangent of x dx. And then I was like, I don't want to deal with it. But actually, now that I think about it, I could go further, right? You can do integration by parts on this, kind of like we did examples 1 and 2 last time, right? Like, check it out. This could be my, let's say, dv2, and this could be my u2, right? And this illustrates an important calculational principle, which is we should use big parentheses when we come to something like this. If you're going to do integration by parts a second time, and there's like a minus lurking out front, put some parentheses down so that you don't get, trapped or tricked by the number of minus signs. It's really easy to do. So what I should put here, and I'm just going to write it symbolically over here, is u2 v2 minus the integral of v2 du2. Yeah? I should put that in the brackets. And so doing that, what's my u2? Well, u2 is x, right? What's v2? What's the integral of secant tangent? Just secant, right? So we have x secant x minus what? Minus the integral of v, which was secant x, and then du2, which is dx. Oh, look at this. What happens here? See, this is something we didn't see yet in any of our examples, so I think it's actually interesting to finish this, because you see what happens is these cancel, and what do you get? You get back the integral of secant x dx. Yeah. True, but useless. Right? What's your name?
Lydia.
What?
Lydia.
Lydia. You're equal to Lydia. There you go. So I've said nothing. Well, I guess I'm saying your name is Lydia. That's something. But I mean, you can't solve the integral with this, right? All you know is that that's the problem you're doing. So anyway, we have to fall back on the u substitution here for now. There is a way to derive that integral I did last time. Let me just remind you what it was. Last time we derived the integral of secant x dx is natural log the absolute value of secant x plus tangent x plus a constant, right? But this was by u substitution. So some of you were like, I know you guys take notes, and sometimes you miss sometimes you only write down part of what I say. If I don't write something on the board, and you're like 4 or 5 minutes behind me and you're writing, then when you get to that part of the board, you just interpret it as a continuous statement. So I had like 3 or 4 people come to me after class last time and say, what were you doing? The point of that example was that integration by parts doesn't work on secant. So we have to fall back on some other weirder method, which in this case is U substitution. All right? So there's that. Now, so there were some problems. I think there's a lot of problems on the quiz. And I think that something that will serve many of you is if I just take 10, 20 minutes of class and just talk about hyperbolic functions, right? And in so doing, we'll have a brief review of Calculus 1, all right? So I think we'll all be better off if I do that. So let's take this, we've got time in here, let's do it. So what are hyperbolic functions? Because it's totally understandable if you had calculus somewhere else or a few years ago and you forgot what these things are, right? It's fine. I personally learned about hyperbolic functions when I got to special relativity, which is a physics course, right? We went up to the professor after class and we were like, Dr. Gould, what is this COSH you're using? What's cosh? What's hyperbolic cosine? What's hyperbolic sine? And he looked at us and he went, what? They didn't teach you that in calculus? He was so sad. Because he's a physics professor. It's not his job to teach us that, you know? But here's the starting point for me. You can take any function, right? And you can write it in terms of this identity. This is a trick. Now, I said any function. That's not quite true, right? What are the terms and conditions for me writing this formula here? What's today's date? The 18th.
X can be negative.
X has to be negative, right? The domain has to be symmetric about the origin, right? If X is in the domain, minus X must also be in the domain for me to meaningfully write that formula, right? There's the attendance sheet. So if you missed it yesterday, feel free to check your name today. I know that it kind of got passed around at the end, right? Okay, so that's just a stupid identity, right? Because you've just added and subtracted the same term, right? See that? And a half plus a half is 1. If you apply this to the exponential function, which certainly is what's the domain of the exponential? What's it look like? Exponential looks like this, right? What's the minus the exponential look like graphically? Like this, right? So it's important to know about those as we do analysis in here, right? You have to have those in mind. Be like me, learn the exponential now if you didn't before, all right? Okay, so if I apply this to e to the x, what do I have? I have e to the x is what? 1/2 e to the x plus e to the minus x plus 1/2 e to the x minus e to the minus x, right? This right here is by definition the hyperbolic cosine of x. This over here is by definition the hyperbolic sine of x. Now, later in this semester, when we talk about parametrized curves and so forth, you'll gain a greater appreciation of why they're called hyperbolic sine and hyperbolic cosine. For a while in here, it's just going to be by means of analogy. Eventually, we'll learn that these parameterize hyperbolas, in the same sense that sine and cosine parameterize circles. So sometimes sine and cosine are called circular functions. These are called hyperbolic functions for very similar reasons. Now, what can you tell me about these functions? How about cosine and sine? Cosine is even, sine is odd. Is that true here? Like even and odd are terms for numbers. What are you talking about? Well, what I mean by that is cosh of minus x is cosh of x, right? And sinh of minus x is minus sinh of x. So that's one of the fundamental things we need to know about cosh and sinh is that cosh is even, sinh is odd, right? What do their graphs look like? So the graph of cosh, what does it look like? Like what? A catenary curve. I suppose that's true. But my more boring answer is it kind of looks like x squared plus 1, but that's not quite doing it justice, right? Because both of the sides, they're both exponential growth, right? So like asymptotically, long term, this is basically what? Like y equals e to the x over 2. And this half of it eventually is like y equals e to the minus x over 2. See, because if you think about it, this formula, right? If x is like super negative, the black curve over here becomes minuscule. It's irrelevant. And if you're really far to the right, the red curve is super tiny, right? So when you look at this formula, e to the x dominates for really, really large x that are positive. E to the minus x dominates that formula for e to the x really large and negative. So on both sides, it's like an exponential divided by 2. That's cosh. What's the range of cosh? The range of the hyperbolic cosine, you guys can tell me, right? What is it? This is its low point, right? That's 1, right? Because cosh of 0 is 1. How do I know that? Well, plug it in, right? 1/2 of e to the 0 plus e to the 0, which is 1/2 of 1 plus 1, which is 2 over 2, which is 1. So there's cosh of 0. What's the range of cosh? It's what? 1 to infinity, right? How about sinh? What's the graph of sinh look like? Well, sinh looks like e to the x for large x, right? And it looks like e to the minus x for super negative x, right? Again, either one or the other of the exponentials is dominating as we get far away from the origin, because the other exponential is tiny. So you can think about it in this way. And so the graph over here, it's going, and what's sinh of 0? See, here's the definition right here. I put 0 in, I get 1 minus 1. E to the 0 minus e to the 0, which is 1 minus 1. I get sinh of 0 is 0. So it goes through the origin, and it looks something like this. So it kind of looks like a cubic, but that's not, that's not accurate. These are both exponential growth on both sides, okay? What else can you tell me about cosh and sinh? Well, let me just finish the algebraic aspect of it before I go to the calculus part of it, okay? What's e to the x times e to the minus x? Well, if you allow me this short manga-style calculation, manga, this is e to the 0, right? Which is 1, yeah? But what's e to the x? Well, e to the x, we just defined it, cosh plus sinh. Yeah, e to the x is cosh plus sinh. What's e to the minus x? Well, it's cosh minus sinh, right? Because the cosine eats the cosh eats the minus, and the sinh spits it out. So this is cosh x minus sinh x. And what happens when you multiply these? What pattern is that? That's a plus b, a minus b, right? It's the difference of squares formula. So this works out to cosh squared minus sinh squared. So this is going to be important for us to know as we try to master calculus on hyperbolic sine and cosine. We need to know that this is the analog of cosine squared plus sine squared for hyperbolic cosine. Yeah.
I don't understand why cosh minus sinh is e to the negative x.
I'm just putting in over here. Check it out. Let's see here. So if e to the x, let me just write it here. If e to the x.
Oh, wait, I see what you're saying now.
Yeah, but I wrote it, so you're going to have to watch me write it again. Because if you've got that question, somebody else has that question, and they haven't figured it out yet. So let me just write it down. See, because I'm just combining two things I wrote on the board, but let me do it explicitly. There you go. Why is this relevant to the quiz? What did I do to you on the quiz? Tortured. Well, if I just asked you questions you knew, it wouldn't have been interesting, right? And although I'd also have to know exactly everything you knew, which would be difficult since I don't know you. But I think I asked you guys a question about the natural log of, what was it? Oh yeah, cosh 3x plus sinh 3x, right? So what is that actually? See, in view of these things I'm showing you, that's actually the natural log of e to the 3x. None of you knew that. You're not alone in not knowing that. None of you knew that. None of you saw that. Right? That's fine. I wouldn't have when I was taking this class either. So that's 3x. Now some of you, when you differentiated that, managed to get 3. But you did it a harder way, right? Because you differentiated the natural log of cosh plus sinh, and you did 1 over that, and then times the derivative of that, and then by the chain rule, things canceled, you got 3. But this is much easier, right? If I differentiate this, I could differentiate that. So the derivative is 3. Yeah? Okay, so yeah. Let's move on to calculus. What's the derivative of cosh? The derivative of cosh is sinh. And the derivative of sinh is cosh. You can see that directly from differentiating the definition, right? And anytime you're asked a question about cosh and sinh, you can fall back on the definition and try to work it out from that perspective if you want, right? Sometimes that's the right way, sometimes it's not. What's the derivative of tanh? What is tanh? Hyperbolic tangent. So here we're looking at d dx of sinh x over cosh x. This is good because it'll give us a chance to review the quotient rule, right? Because the quotient rule is the only way to really derive this here. Yeah? I mean, there might be another, but nothing I should do. So I do what? I do the derivative. Let me use prime notation, if you don't mind. So this is sinh prime times cosh minus sinh times cosh prime, all divided by cosh squared. Now, how's that work out? So what you got is you've got cosh cosh, which is cosh squared. And over here you got sinh sinh, which is sinh squared. And that's divided by cosh squared. So what's that get you? Well, remember, we just proved that cosh squared minus sinh squared is 1, right? So we've got 1 over cosh squared, also known as hyperbolic secant squared, which I have like such, I don't know, I just say hyperbolic secant. I've got no good way to abbreviate that. So the derivative of hyperbolic tangent is, in fact, hyperbolic secant squared. This is kind of like tangent, right? What was the derivative of tangent? It's secant squared, right? But for kind of different reasons, right? Because when you differentiate tangent, you got sine over cosine. What happens there? You get a what? You get a plus. You get a minus in the derivative of cosine. That minus and this minus cancels, and you get sine squared plus cosine squared is 1. But it's almost the same calculation, right? Okay, so any questions about anything here? Natural question asked, what's the graph of hyperbolic tangent? What's that look like? So if we look at tanh, that's what? That's e to the x minus e to the minus x over e to the x plus e to the minus x, right? Because that's sinh over cosh. Where'd the halves go? They canceled, right? I just canceled the half out front in both. How does that formula behave? Let me explain to you here. There's 2 different ways to simplify this. The one we could do is we could multiply the equation by e to the x top and bottom, right? If I multiply the equation by e to the x top and bottom, I get e to the 2x minus 1 over e to the 2x plus 1, right? On the other hand, I could take that equation and I could multiply by e to the minus x on the top and bottom, right? And that would simplify to 1 minus e to the minus 2x over 1 plus e to the minus 2x. Both of those formulas are important because they immediately reveal to you the limiting behavior of the function. How does hyperbolic tangent behave when x is very, very large? Which one should I look at when x is very, very large? Yeah, e to the x dominates, right? So this is actually kind of not helpful. So actually, the larger point is this. E to the minus 2x goes to 0 for x going to infinity, right? And e to the 2x goes to 0 for x going to minus infinity. Those are my linchpins for this analysis, yeah? So if I look at this formula right here, for x large and positive, this just goes to what? 1 minus 0 over 1 plus 0, which is equal to 1 as x goes to infinity, yeah? Because the e to the minus x drops out. And the other one there goes to what? 0 minus 1 over 0 plus 1, which is equal to minus 1 as x goes to minus infinity. So apparently, this guy has got graphs that have horizontal asymptotes at plus or minus 1. And what the graph then looks like is something like this. There you go. That's y equals tanh of x. Its range is minus 1 to 1, not inclusive. What's the derivative of tanh? Hyperbolic secant squared. We just worked it out, right? Is that always positive? It is, right? Because is the 1 over the cosh positive? Well, anyway, it's the square of a function, right? And that function's non-zero, so certainly it's always positive. Hyperbolic tangents always increasing. These are things we can discern from calculus 1, right? Positive derivative increasing function means the graph's always going up. All right, let's move on here. What else do we have to deal with? What about inverse functions? Well, so let's see here. What would the derivative with respect to x of inverse tangent of x be? What's the derivative with respect to x of inverse cosh of x? Let's work on that one. All right. If you don't know these, how do you figure them out? There's a simple process if you forget. So we do this, is y equals inverse cosh of x, like so. All right. Then I take the hyperbolic cosine of both sides. This gives me cosh of y equals to cosh of cosh inverse of x. What's that give me? That just gives me back x again, right? So, yeah, x. Now what can I do? Well, you see, I've got cosh of y equals to x, right? So I can say the derivative, I can differentiate what's called implicitly, right? Differentiate both sides implicitly. And what happens? Well, the derivative of cosh, we just said, is sinh, right? But I'm differentiating a function of y with respect to x, which means I have to apply the chain rule. So this gives me sinh of y times dy dx is equal to, well, the derivative of x with respect to x. You know, if you're ever teaching calculus and you want to shame the students, you should bring in a kindergartner and teach it to them, that kind of thing, you know. It's 1, right? You'd be like, of course it's 1. The dx's cancel, right? That's not entirely a lie. Like, there's a way of formalizing calculus to make derivatives actually quotients of numbers. The fine print there, though, is that the numbers have to be part of an extended number system called the really long line or something like that, which adjoins infinitesimals to like real numbers. And so while it seems simpler, it actually adds this like burden of like really complicated abstract algebra at the start of calculus, which I think is a bad choice. So we don't do that. But there are people who believe in it because they hate limits so much. So you can get rid of limits if you're willing to work with really abstract numbers called infinitesimals. Newton called them fluxions. They've been with us from the start. But here, dy dx is 1 over sinh y. Though that's no good to us. We want a formula in terms of x, right? How do I convert the sinh to cosh? What's the rule? Remember? Cosh squared y minus sinh squared y is equal to 1, which means sinh squared y is equal to cosh squared y minus 1, right? So you take the square root of both sides, yeah? What's that give us? That gives us that sinh of y is plus or minus the square root of, what was cosh y here? Remember, cosh of y up here, it was equal to x, right? So that cosh of y I can replace with x. So x squared minus 1. Algebra, though, says plus or minus. How do I choose? What is it? Is it plus? Is it minus? How do I decide? So algebra has led us to this. Dy dx is equal to plus or minus, well, 1 over, let's say, plus or minus the square root of x squared minus 1. How do I choose the plus or the minus? Which one is it? And why do I choose that? What's the relation between a function and its inverse function in terms of differentiation? Do you know? What's the relation between a function and an inverse function? Like this, right? F of f inverse of x is equal to what? X again, right? Differentiate that, what happens? Differentiate it. So we get df dx times what? That's evaluated at the inside function, which in this case is f inverse of x, right? Times the chain rule, which is the derivative with respect to x of f inverse of x. What's that equal to? The derivative of x, right? Which is what? 1, as we were just talking about a second ago. What does this say? What this says is simply this. The product of the rate of change for the function and the rate of the change of the inverse function evaluated at respectively the point x and the point f inverse of x, their product must be 1. That means that the rates of change have to be reciprocal, appropriately evaluated. More than that, they have to have the same sign. If this is plus, this has to be plus. If this is minus, this has to be minus. So I just erased it. Oh man, of all the so this actually begs the question, which hyperbolic, so this was the graph of cosh, right? Is that an invertible function? When is a function invertible? Do you remember from pre-calculus? We had to have what? Oh man. Shut up. You know, as I was telling my other class yesterday, like there's no end to numbers in like North Carolina I need to block. And it's so boring, it's just dead space, right? Like I was telling them, I used to get these extended car warranties. It was at least interesting, you know? Never had a warranty really, but so this is not invertible globally because it does not pass the horizontal line test, right? It is not a one-to-one function, right? Check it out. Don't fails. So what do we mean inverse hyperbolic cosine? It's not even invertible. It's a choice, right? And the standard choice is that when you're calculating the inverse hyperbolic cosine, you're actually talking about the inverse of the restriction of the function to this part. Okay, so like this is the, so really, if I was to be more obtuse, I would say cosh restricted to 0 to infinity inverse is equal to cosh inverse. That would be more honest. All right, just like inverse cosine, right, is actually this. Cosine restricted to 0 to infinity, wait a minute. Yeah, 0 to pi is equal to inverse cosine. Because that's the domain which we restrict cosine on which to give it an inverse. Because of course cosine oscillates, right? It doesn't have a global inverse. Okay, so with that said, this is the part of cosh that we're inverting. Is it got a positive or a negative derivative? Positive. So what does that mean over here? We must choose the plus. That's the point. So all of that to tell you that we choose the plus, and this gives us the derivative with respect to x of inverse hyperbolic cosine of x is equal to 1 over the square root of x squared minus 1. Now this is relevant. Why? What happens? Let's take a step back into sine, cosine, tangent for a second here, yeah? Let's talk about that. So tangent like this, sine is like this, cosine is like this. These are the parts of cosine which are inverted, parts of sine which are inverted, the parts of tangent which are inverted. Inverse sine, inverse cosine, inverse tangent, these are all local inverses, right? Like, of course, you know, it goes on, yeah? The functions, right? So when we talk about inverse sine, inverse tangent, inverse cosine, it's with respect to those restrictions. And what did we learn before? Do you guys remember? The derivative with respect to x of inverse tangent of x was what? A lot of you remember this. 1 over x squared plus 1. All right. What's the derivative of inverse sine? Now, the reason I didn't put a minus there is, remember, we're inverting sine with respect, look at this. So it's this part is the sine, we're inverting this part, right? It's increasing there. It has to have a plus because the sine of the inverse derivative, the inverse function's derivative must be the same as the sine of the function which we're inverting. But on the other hand, cosine, inverse cosine, see, inverse cosine really, it's got the same shape as inverse sine, right, in some sense. And so that one actually is exactly what you said. So like inverse sine and inverse cosine, they're kind of the same function. Not exactly, they're, you know. Anyway, so this has relevance to what? Like I had a problem on the quiz, which was what? Integrate, what was it? 1 over the square root of x squared minus 1. I forget which one was, let's make it a little bit different. Let's make this one like 7 here and 13 over here just to make, it's not the quiz problem. I don't remember the quiz problem off the top of my head. But it was like this. So which one's inverse cosine or inverse sine? Which one's an inverse hyperbolic? Well, this one has to be the sine or cosine, right? Because the domain of the inverse sine, the domain of the inverse cosine, it's the range of sine and cosine. What is the range of sine and cosine? -1 to 1, right? Think about this formula. It does not make sense except in the case that x is between -1 and 1. In contrast, this over here, try putting in a half, what happens? Try putting 0. You get the square root of -1, right? That's complex, which we could make sense of, but not in this class. But anyway, so this has to be the hyperbolic one. This one has to be the regular one. So the answer here would be like 7 cosh inverse of x plus 13 inverse sine plus a constant. There would be the integration. Now, if you're rusty on this stuff, like no big deal. Like I understand. Like I don't think it's like, oh man, you don't know that in quiz 1. I guess all hope is lost for you in this course. No, of course not, right? This is something you're learning. And that's why I'm reviewing this today, because I think you probably, some of you have not seen this stuff in Calculus 1, right? Any questions? Let's see here. So how would you calculate the derivative of inverse hyperbolic tangent? Let's do one more of these just to try to, because I feel like this is a skill some of you are missing. If you don't know, I mean, so you got two choices, right? The one choice is to look at all 6 derivatives of the, like you've got inverse cosh, inverse sinh, inverse hyperbolic tangent, right? You've got inverse cosine, inverse sine, inverse tangent, right? So you can just memorize the derivatives of all those, right? But that's a lot to memorize, right? It's good to have a backup so you can derive it. Here's how you do it. And so like, I take the hyperbolic tangent of both sides. Then my next step is differentiate implicitly. The derivative of tangent is secant squared, right? Hyperbolic secant squared, we learned that. So we get hyperbolic secant squared of y times dy dx equals to 1. I solve for dy dx, what do I get? 1 over hyperbolic secant squared y. Now we've talked about the identity for cosh squared and sinh squared. What's the identity for tangent hyperbolic secant? I'll put it over here since you guys are over here. Let's see here. So we have cosh squared minus sinh squared x equals to 1. What happens if you take that identity and divide by, let's say, divide by what? Just divide that by cosh squared, yeah? What happens? Then you get cosh squared over cosh squared over cosh squared minus sinh squared over cosh squared equals to 1 over cosh squared. But what is that? What you're looking at there is 1, right? Sinh over cosh is tanh. We can bring the square out, right? So we get 1 minus hyperbolic tangent squared x equals to hyperbolic secant squared x. So that's the analog of secant and tangent identity for the hyperbolic. So this one here, what is that in terms of tanh? Hyperbolic secant squared is giving you your work. You're getting to work on now. So, hey, I guess I just need to take this x and make it a y, right? For that over there. So we get what, 1 minus, maybe it's helpful if I just erase this down here and make that a y just for your reference with respect to the other question, yeah? So I've got the hyperbolic secant squared y over here, which is apparently what? Rats. Is it, now here's, I can't see that, right? Is it 1 minus x squared or is it x squared minus 1? And how would you figure that out without looking at that? What's the domain of inverse tanh? It's the range of tanh. What's the range of tanh? Minus 1 to 1, right? We had that graph over there. The range of tanh is minus 1 to 1. X squared minus 1, is it positive or is it negative if I put in minus 1 to 1? It's negative, right? X squared minus 1, if I plug in 0, I get negative 1. So it must be 1 minus x squared that I put here. It must be 1 minus tangent squared y, which is 1 minus x squared. So what I'm trying to tell you is that there's a circle of related ideas here that you know, they'll help you keep track of what the sign is and how these different things work together if you'll just take a second and sort of appreciate all the interlinking ideas between the graphing and the calculus and everything else. So yeah, the derivative of inverse hyperbolic tangent is 1 over 1 minus x squared, right? So that's kind of cool. All right. Any other questions? Yep.
When you went from tangent y to secant squared y, the antiderivative.
Oh no, here I just differentiate implicitly. And I say differentiate implicitly because I don't have y equals formula, right? I've got a formula of y equals to another expression. So whenever we differentiate something where y isn't sitting out there, y equals stuff, we call it implicit differentiation, right? Now there are other weirder things to know about in terms of inverse, the inverse hyperbolic functions, but I think I have done enough of that to you today. So let's call it. Let's stop there for the hyperbolic functions. I think I've told you the main things to know about them. Yeah. Shall we foolishly try to do Dr. Sprano's problem? Like tomorrow, we're going to come back and do more integration by parts. Okay, I'm not done with integration by parts. Have no fear. It's like I'm not moving on. I have devoted several days in the schedule to integration by parts. I just thought that I think that like there's a gap in a lot of your knowledge about hyperbolics. So I thought let's just take a day and make sure we've all seen these things at least. Yeah. I'll eventually figure out how to record this thing in Teams. I don't know. I'm supposed to be recording this class in Teams, which is irrelevant because we have this, right? But, you know, you have a one-size-fits-all policy. You can't, like, try to argue with logic. It confuses them. See here, unfortunately, that is more and more the whole of society, and we're willing to embrace these things. Too many people. All right, where am I? 132, right? Here we go. Again, you don't have to do this if you don't want to, but feel free. Again, I'm assessing like attendance with the attendance sheet. Whether or not you do this is up to you. I don't really care. I'm just doing it. Let's see here. What else? Oh, yeah. So let's try Dr. Sprano's problem. I feel like this is going to be just enough time to get stuck on it and leave us wanting more, right? I'm going to put my eraser. All right. So I was going to say, I think if you guys have, if you had trouble on the quiz with the differentiation, like it is important to go back and just like work review problems at the end of a chapter or something until you like refresh your memory. Nah, I refuse. I refuse. We're not going to try that one in class today. I have.
Do we need something else for it? Like conference-wise?
It's just going to be just enough time for me to start it and get confused on it, and then we'll be out of time. So it's not it would not be wise. You can turn off the camera. Oh yeah. So yeah, you got it. You just press it in. Did it beep? Here. It's just this.